And I want to thank our sponsors again, Lennox, Advantix, Mechanical Star Systems, and Texas Air Systems, yes, and Schneider Electric. Thank you so much for sponsoring today's workshops. This has been a wonderful, wonderful workshop. I've heard nothing but great reviews so far from our audience and the presenters. So I hope that you enjoy your lunch, but I do want to ask that you provide your undivided attention. We will be listening to our next presenter. And again, we have another system for you to consider, for you to review so that you can see how these systems could apply to your projects, your facilities, to your sustainable practices. Our next presenter from Advantix Systems is Mr. Trevor Wende, and he is the Vice President of Marketing for Advantix Systems Manufacturers, one of the world's most efficient air conditioning systems. Advantix Systems innovated liquid desiccant, am I saying that correctly? Desiccant technology allows industrial and commercial customers to control humidity, improve indoor air quality, and reduce their energy costs by over 50%. Prior to joining Advantix Systems, Mr. Wende was a McKinsey & Company where he worked primarily in the firm's energy and sustainability practices and worked extensively on energy technology and energy efficiency opportunities. Mr. Wende has a bachelor's in mechanical engineering from UC Berkeley and a master's from MIT's Sloan School. Please help me welcome Mr. Trevor Wende.
Thanks for that introduction, and thanks for the opportunity to come here today to present. What I'd like to start with is actually a simple question. Who here has heard of liquid desiccant air conditioning before? Okay, so we got look like about 5%, 6% now, maybe 7%. So it's not well known. And that makes this presentation and my opportunity to come here that much more enjoyable for me. And let me first say that you shouldn't feel bad. I started looking at liquid desiccant technology 2 years ago in my role at McKinsey & Company, looking at the broad space of energy technologies. And this company came up, and I had never heard about liquid desiccant technology. When I had finished learning about liquid desiccant technology, I joined the company. So I'm not expecting all of you to join the company, but I suspect you will be equally interested in the technology and might be able to find Control-Alt-Delete. I need a password. Let me just go on. You will hopefully be as equally interested in the technology and maybe find use for it in your facilities and the designs and the implementations of HVAC technology that you use. Let me just, since we don't have the visual right now, I'll give you the layout of this presentation. Basically, it's in 3 parts. The first and sort of the most general part is just about humidity and air conditioning. And it's fundamental to cover that because if you don't know what part humidity plays in air conditioning, you won't know, I'll just clip this on, you won't know why you would use liquid desiccant as an air conditioning solution. So then we talk about the alternative that liquid desiccant provides when you are talking about humidity and air conditioning. And then finally, I want to go in, I have a short video and some graphics about how liquid desiccant actually works. I want to keep this interactive. I'm going to ask you guys some questions. I am fully welcoming any raised hands. If there's a point that I made that you want to clarify, if you want to disagree with, if you want to discuss that point further, we've got the time to do that. So please don't be shy. Just put your hand up and we'll hit that right there. And of course, time at the end to answer any questions that can wait for later as well. So let me talk first about humidity and air conditioning. So humidity and air conditioning typically is the sort of the forgotten stepchild, because what you look at when you see a typical building's design load is you see this big, what you'd call the sensible portion of the load, which is temperature reduction. And you've got this smaller humidity removal portion, which is called the latent portion of the load. And by the way, what's not shown there is you've got a control system and a readout which reads temperature. And that's what everyone is thinking about. It brings it really top of mind. Virtually everyone can tell you what temperature they set their home air conditioning system at. Very few people can tell you what humidity on average it is in their home or what humidity that system is controlling to. However, it's really a hidden part of the overall cost of the system, and it's really something that causes a lot of energy usage, and I'll describe why. If you look at the conventional air conditioning process, you take this overall load that the air conditioning system needs to take care of. You feed it into that air conditioner. You've got direct treatment of that temperature reduction. You've got a cold fin on a coil touching warm air moving by. It cools it directly. It's just thermal transfer. And depending on how efficient that heat pump or heat removal system is, we saw a SEER or IEER 21.6 system that they talked about earlier. You can get rid of that sensible heat very efficiently. However, you talk about the humidity, and that same metal fin has no ability to directly extract moisture from the air. However, you still need to do that. The air that you're bringing in from the outside, the humidity that's coming off of your body, other point sources of humidity in a building are all going to create a rise in humidity unless you also control humidity with your air conditioning system. And it represents here about, let's say, a third of the overall load. But the way that it's dealing with that is an indirect process. You are overcooling the air until you get to a dew point, and that dew point basically represents the amount of humidity that you want in the air. Let's say this room might be a 55-degree dew point. But what you've done is overcooled to the point where that air can no longer hold that moisture, and it condenses out. It condenses onto the surface of that coil and eventually will drip away. Well, notice that last thing I said is that humidity, these big droplets of water go directly onto the surface of that coil. Well, that actually interferes with this direct process as well. So the more of this humidity that you're taking out, the less efficient this overall system becomes. So what you have is you have traditional systems which are good at dealing with the temperature reduction portion of air conditioning and very weak at dealing with humidity. And somebody had asked the question earlier when they were talking about variable refrigerant systems, variable refrigerant flow, if you need direct or if you need an outdoor air or a dedicated outdoor air system. And you absolutely do, because those systems actually are even less able to deal with the humidity portion of the load, so you really need to treat that humidity source of your outdoor air. I'll get into that application as we go along. Okay, so what is the problems that you see associated with humidity in air conditioning? Well, it drives a lot of maintenance issue. That's a frozen evaporator coil. A lot of people in humid parts of the world have seen those. You get a lot of mold, bacteria, microbial growth that is promoted by the presence of moisture in your air conditioning system. So if anybody's pulled out an evaporator coil that's been in a house and never cleaned for 10, 12 years, it's usually pretty disgusting, and that's what you're blowing all of your air that you're circulating your house over. You have systems that are not adequately dealing with that, causing musty odor, high humidity environment. You have systems that are dealing with humidity in a bad way, which is too much of that overcooling, and you create freezing conditions. Everyone's been in a movie theater or a packed hall where it's been about 48 degrees in the middle of the summer, and you need to bring your overcoat just to sit through the 2-hour movie. And then finally, you drive a lot of your electricity costs up by inefficiently dealing with the humidity portion of the load. So let me talk a little bit more. I talked about the sort of 2/3, 1/3 breakdown of humidity as a portion of your overall load. Historically, that has not always been the case, and this is essentially the problem that most people are running into. You started from a base in the 1980s, and this, if you think about the average mechanical engineer that's putting his stamp on a building, when they graduated college, I would say, you know, the average person was coming out of college right around this time. And what was happening at that time is you didn't need to introduce a lot of fresh air into a building. And the loads inside of the building were very inefficient. So a lot of incandescent lighting, a lot of glass or windows, glazed buildings that were bringing in a lot of sunlight. It was not a low E glass like we have today. No one had ever heard of Energy Star appliances. No one was concerned about energy efficient motors in industrial facilities or fans or any of that stuff. So that sensible load, I keep hitting the wrong button here, that sensible load made up, this is a fraction, made up over 80% or 0.8 of the total load. So that's what we call the sensible heat ratio. So that means 80% or greater of what you're doing there is temperature reduction, and only that remaining 20% is going to be humidity removal. Well, what happened? Well, at one point the standards have increased the ventilation rates. You keep getting more efficient appliances. So this relates to ASHRAE standards 60 and 92.1. And you eventually start seeing that over this selection of cities, if you're in a reasonably humid geography, and I guess this might be the closest analogy for us here at Fort Worth, or maybe Atlanta was brought up earlier, you're no longer up here in that area where it's 80% sensible or 80% temperature reduction. You're talking more between about 3/4 and 2/3. And by the way, this trend will continue. Energy efficiency improvements will always move this line down because they're always addressing heat loads in your buildings, whether it's the fans that we talked about earlier, whether it's energy efficient lights, low E glass, all of those things reduce your sensible, and none of them reduce that latent or that humidity portion of the load. And by the way, if you get a sensible heat ratio below 0.75, which never used to be a problem, you will start to struggle. Why are you going to struggle? Well, over that same period of time, what changed in your average air conditioning unit? Somebody throw something out there. What changed?
The color.
I think they got better graphic designers, because that certainly looks more attractive in their brochure. It's a really similar system, and I'll put a caveat on that in a minute. But typically, and the thing that I care about is they're designed to operate at that same sensible heat ratio. And that goes for your packaged rooftop systems. They became a little bit more efficient. The ones that are mass produced became a little cheaper by the ton. But they're really the same stuff. And it really shows in that they really didn't have to change their design a lot over a 25-year period. So I say that a little tongue-in-cheek, or the caveat is we do have a lot of these nice advances. We talked about variable refrigerant volume, variable air volume systems, which are becoming more and more common. You have, for example, chilled beams, a very progressive technology. All of those technologies are actually even less able to deal with the humidity portion of the load, because they're focusing on what is considered to be the big prize, which is the thermal portion or temperature reduction. So those have a sensible heat ratio of 90%, 95%, and some of them, chilled beam for example, can only deal 100% with the temperature reduction and not at all with the humidity reduction. So that still leaves us with this big humidity reduction problem. And by the way, if you are not in a typical building, which is what that graph was illustrating, you're going to have an even bigger problem. So what's not a typical building? Well, if you have high ventilation requirements, if you have to get to a lower dew point than 55 degrees, if you have an internal humidity load like a pool or a fitness center or someplace where people are working out and sweating, You have high ventilation requirements. This is going to resonate with a lot of people here. You've got schools, auditoriums. The room we're sitting in right now, this is high ventilation requirement because of the density of people and all the fresh air that we need to breathe in order for the CO2 not to go up and for you not all to get drowsy and fall asleep during my presentation. So there's a lot of places where you're going to be even in deeper trouble, and what that's led to is people buying specialty equipment. So typically you're not going to get people that are buying this standard rooftop for all of their needs. And that's a good thing, that's progress, but the specialty equipment they buy tends not to be very energy efficient. Now let me talk about what that equipment is. I already talked about this off the shelf. This is your package rooftop system. Hasn't changed much in 25, 30 years. The problem here is that that doesn't have the capability to deal with the humidity load. Doesn't stop some people from trying, and the symptoms we see a lot in South Florida where I live is you get sick buildings because you have really high humidity because the humidity wasn't removed. Or even more commonly, we have buildings where people went and they identified the source of the humidity problem, which was the fresh air, and they eliminated the fresh air. And I'm not kidding. I think that's probably 2 out of 3 buildings that we see in South Florida if they have systems that have been around for a while. And you know, the logic makes sense. Unfortunately, the people closing off the fresh air don't answer to the people who actually have to breathe the air inside of that building. So that's really not a good approach. So what can you do instead of that? Well, we've got these dedicated systems. A dedicated system, or people will say DOAS, dedicated outdoor air systems. It's a dehumidifier. It's all the same equipment, just depends on where the air goes in and out. It's still using overcooling like we talked about, but now you've got a big coil. You're putting more tonnage of refrigerant into a smaller volume of air. And you have maybe a specially designed coil that can accommodate more of that condensation on the surface of the coil. And that will effectively go well beyond that 0.8 or even 0.75 ratio of temperature reduction to humidity reduction. But, it's a big but, it's expensive. And it's not just high first cost, it's expensive to maintain. There's a lot of parts there. Typically involves a hot gas reheat, other parts that are prone to failure. And there's a very high energy cost. You are overcooling, and then you're adding heat back into the air that you're introducing to a room that you're air conditioning. I'll talk specifically about the energy differences in a second, so let me hold on that. Well then, if you were really being extreme about it, you would go to a solid desiccant. A solid desiccant no longer uses this overcooling approach. This is a pretty it's a pretty common piece of technology, but people would, in let's say the commercial and institutional sector, usually wouldn't use these because what this is doing is it's removing humidity through what amounts to be heat addition. It's not direct heat addition. We are gathering that you're gathering that humidity directly through a chemical absorption process into a desiccant and adding a bunch of heat into that desiccant then later to drive off the humidity that's collected. Eventually, however, a lot of that heat ends up back in your building because that wheel is rotating back and forth. And unfortunately, that seems like a very direct and elegant approach, but what it amounts to, and I'll show you the energy graph in a second, is a very high energy consumption. And by the way, these wheels themselves are prone to breaking down. It's a brittle material that you're heating, cooling, heating and cooling. And if you think about the mechanics of that you're expanding, contracting, eventually that wheel disintegrates. So that typically in 2 to 5 years needs to be changed out. That's 30% again the cost of the first cost of that system. So we haven't got a good solution here in what I would call the traditional set of pieces of equipment that people would buy to deal with the humidity problem. That's where I want to introduce liquid desiccant. And I first want to talk about the energy advantage of using liquid desiccant. I'll get to why it's not costly from a first cost perspective in a minute, but really I want to talk, and I know there's a lot of numbers on this slide, it's a bit of an eye chart, but what I want to focus on is You're doing a couple of processes typically when you are doing this air conditioning. Now this is that conventional system like either the off-the-shelf or the DOAS using overcooling. So you've got a first process which is a cooling coil which needs to get down to a low dew point temperature. So what I've done is I've calculated, I've dropped the footnote off this slide, but this is for 3,000 CFM of outdoor air being introduced in the Boston design condition day. So all of these numbers, by the way, in the Valley design condition day are going to be much higher. So here we've got 217,000 BTUs of cooling that are required. BTUs per hour, all of this is. And then you have to add reheat, otherwise you're overcooling that space. So now you're reheating to the tune of 74,000 BTUs. So you're consuming overall just shy of 300,000 BTUs in order to get the air that you're going to supply into that space. Solid desiccant is a more energy intensive approach, in fact, even than that conventional, because the first process is this dehumidification, which requires all of that heat addition. So we're talking about 250,000 BTUs in a typical desiccant wheel in order to drive off that moisture. And then you've heated that air, so now you have a post-cooling process of 193,000 BTUs. So at the end of the day, you've added that together and ended up with almost 450,000 BTUs to treat that 300 or 3,000 CFM of fresh air. So bring in liquid desiccant. There's still two processes. First is a liquid desiccant cooling process. That is a cooling and dehumidification simultaneously. We're using a cold desiccant solution. And I'll get to what a liquid desiccant is, but we're using a cold desiccant solution to directly reach the point at which we're supplying the air. So that is actually taking a bit of a shortcut there. So instead of 217 to get down to a 55-degree dry and wet bulb temperature at the dew point, we're getting to the right wet bulb temperature or the right humidity level at a warmer temperature where you're actually going to supply it into the room. So 142,000 BTUs, and that eliminates the necessity for the 74,000 BTUs of reheat. Now you still have to regenerate the desiccant, and so this desiccant dehumidification energy is there. However, liquid desiccant needs much less energy to regenerate, so you're actually using the waste heat coming off of the condenser of that cooling process. So you've got 142,000 BTUs. You need about 200,000 BTUs, or just shy, let's call it 180,000 BTUs in order to regenerate that desiccant. And this is actually about exactly what you get off of the condenser with a typically efficient heat pump being involved in that process. So let me sum that up, and then I want to pause for questions on this one because it's a pretty complex slide. So we've got 142,000 BTUs compared to 291 or 445, and that's the dark blue boxes here. So we're using a third to a half of the energy that would have been required to remove that humidity under the conventional approach. This is sort of, there's some optimization that you can get, and in particular you can use condenser reheat for some of that solid desiccant dehumidification. It's a little bit beyond the scope of this presentation, but I did add the lighter blue bars here, which are represent a more optimized system. But you can see you can also further optimize the liquid desiccant system because of the moderate temperatures it operates at. And you can still beat them basically by a half or even 2/3 of the energy that it would cost to do it the conventional approaches. Any questions on this? Go for it.
You're pulling sensible as well as latent in your first process?
Yes, exactly.
So that's a cooled desiccant.
It's a chilled desiccant. That's exactly right. Yep. Now, let me just fast forward. Well, let me hold that question because oftentimes in order to optimize a system, we'll incorporate a post-cooling, pre-cooling processes as well, which you would in the solid desiccant systems commonly do that. But it's not essential to the process. You can achieve both the cooling and the dehumidification that you need simultaneously using that chilled desiccant. However, you might be able to do it more efficiently. What I'm not representing on this slide is what is the COP of achieving each of these amounts of enthalpy change. But you can achieve that 142 using a higher COP, or with a higher COP if you use maybe multiple heat exchangers. And I'll go through the details when I got the diagram up. Yep.
On the liquid desiccant, you need to take air to the dew point temperature. Is something else different?
No, you don't, and that's the beauty, is it's a chemical attraction. So you're directly extracting via what on the chemistry level is a polar attraction between what's salt molecules in the desiccant and the free-floating water molecules, which are vapor at that time. Another way to say it is that you are actually bringing the dew point down, way down, or you're bringing the vapor pressure down so that you've actually gone beyond the natural dew point of that water vapor, even without bringing it to such a cold temperature. Okay. So that's sort of the chemistry of it, but what you really need to think about is, in the practical implementation, what that means is I can reach the same level of humidity at 70 degrees and never go below that as this equipment needed to go to 55 degrees to reach. And that has multiple benefits. Is that a question or just adjusting your sleeves? Just adjusting sleeves, okay.
The benefit that's in, when you extend your benefits, you said it has multiple benefits in.
Yeah, there's multiple benefits beyond the energy consumption, which is, I think this is always the primary concern. We're reducing the amount of energy that you need to input into that system. There are some other benefits which I'll cover in a later slide that have to do with air quality, maintenance, and things like that. Okay, let me move on. So then the question naturally becomes, what is a liquid desiccant air conditioning system? So I've selfishly included only pictures of this is Advantix Systems liquid desiccant. We're not the only manufacturer of those, but we are the only ones that I had pictures of. So that's what you get on this one. But what you see, the 3 points I like to make on this slide is, for one thing, a liquid desiccant is a box. It is a box where you are introducing air that you want to treat, you're performing a process inside of the box, and then you're pushing out using a fan that air into a ducting system or into your space directly that you're trying to distribute and treat the load of that building. Not a very attractive box, I'm freely admitting that, but it's just a box that integrates like any other component of your air conditioning system, and think of it as an air handler or DX unit. Secondarily, people like to think about where they would put it. Well, you can see obviously this is rooftop mounted. This actually was we pulled a 25-ton rooftop right out of that same spot, put this on the same curb. We've got an indoor installation. This is treating a fitness center. We've got obviously outdoor pad-mounted installation, so that's just graded terrain. We've got literally an installation where this was a retrofit and we shoved it in the closet. This is a nursing home facility and they have a cafeteria or a restaurant in the nursing home, which was having humidity problems. So we brought this in as supplemental humidity reduction capacity, and it's flexible enough that we tied it into their air handling system by just sticking a small unit, this is the smallest one we make, into an unused closet in that facility, and those doors will close and you never even see or hear that unit. And then finally, this is actually the most interesting one, where we've got a small unit tied into a rooftop unit. And this is about 3,000 CFM going into a 20-ton rooftop unit. And what I like to point out about this is a very good solution in terms of energy efficiency. What you've got going on here is you've got fresh air coming in via liquid desiccant. This happens to be a very humid climate. Fresh air comes in via the liquid desiccant that addresses 100% of the latent load, the humidity removal, and cools it to some degree, and then feeds that pre-treated, now dry air into the rooftop, and that rooftop is now only dealing with sensible cooling or temperature reduction. So that rooftop will still control the temperature of the space, but it's doing it more efficiently. Not only did you get rid of the latent load more efficiently, but you're dealing with the room load more efficiently, because that rooftop is now operating at higher CFM per ton. So that means higher coil temperatures, so higher COP. And it's also operating with a perfectly dry coil. So 100% surface effectiveness on that coil. And by the way, you never have to go chemically scrub that coil. It is always clean. So one criticism or potential criticism people will say is, well, you've used two pieces of equipment to accomplish what I could have done with one. I could have just stuck a rooftop there and had the rooftop process both the recycled air and the fresh air. And that's a very common approach. And my answer is, yeah, that's a 20-ton rooftop right there. If you do the math, in order to process that fresh air on design day and the recycled air on design day, you would have needed a 50-ton rooftop. So go ahead, buy a 50-ton rooftop, or you can buy two small pieces of equipment which are more easily mounted up there. They're easy to tie together. It's about the same cost, if not less expensive up front, and you're using 40% less energy over the course of the year than you would if you let that 50-ton rooftop inefficiently chug away at that latent load. Okay, so what is liquid desiccant? That sounds like an oxymoron. Liquid makes things wet, desiccant makes things dry. Who can tell me what this is? That's close. The Dead Sea. If you were closer, is a giveaway. He's reading the Israel Travel Guide. That's the book he's got in his hand. But either one works. And the reason you knew this is because this gentleman is floating unusually high in the water so that he can actually read a book while he's just sitting and lying back. Why he's sitting unusually high is because that water is very dense. It's got a lot of salt dissolved in there, and it's various kinds of salt, but it's about 30% saline, whereas if you look at normal seawater, it's about 2 to 3% saline. So this is 10 times at least as saline as normal seawater, and that makes him float very high. The density is not what's interesting, though. What's interesting is the Dead Sea is a liquid desiccant. What's happening in the Dead Sea is that it's sufficiently salty that the salt that's even dissolved already in water still has an affinity. It still has an attractive force for additional water molecules. So everyone has seen the attraction of water to salt when you've left a salt shaker outside on a humid day, or you've seen people that have to put rice in their salt shakers because it's an outdoor seating at a restaurant, for example. Well, salt can attract a lot of moisture. In fact, the strongest salts can attract 25 times their weight in water molecules. Well, this has about 2.5 times its weight of water that it's dissolved in already. So that means that 90% of the attractive capacity or of the affinity for water is still available. And instead of salt, which is a dry desiccant, like those solid desiccant wheels we looked at earlier, now you have a fluid. And fluids are great because you can work with them. We can chill the fluid, bringing up your point again. You can't chill a solid desiccant. We can use that fluid to transfer between one location to another. We can use that to transfer energy, we can use that to transfer heat, and we can use that to transfer water. So that's the fundamental benefit of a liquid desiccant, and that's the breakthrough. I call it a breakthrough. Liquid desiccants were first used in the 1920s. Well, somebody came along with a more convenient system than bringing the entire Dead Sea in order to dehumidify your space, and that guy's name was Willis Carrier. But what Willis didn't take into account is that someday energy was going to become very expensive. And what the elegance of this system is now it uses much less energy to do what that same Carrier system could have done, or actually does do in many cases today. But we still have to take that whole Dead Sea, and we've got to get it into into a package that you can actually use. So I've got a short video. Ignore this first part. That's sort of just the marketing fluff because we put this up on our website. That's what one of those systems looks like in an industrial application, just as an example. But what I've got in this video, I'm going to talk about the principles of how this works in great detail. How you take the Dead Sea effect and how do you put that into a box that you can actually use and mount on a building. So it all starts out with principles of balance. And this is graphic illustration of balance. I don't know what it has to do with grass, but it looks nice on the website. So we're taking water, starting off with pure water. We put that into a cup. So I'm going to just make a absorber, the Dead Sea effect, and I'm going to make that by adding salt. You see, I don't know if you can see in the back, but there's salt molecules or salt grains dropping in there. And now I've got a salt solution, a very salty solution. What's happening now is I'm actually then absorbing some of the water vapor, and again, it's a little bit dim, I'm not sure if you can see in the back. I'm absorbing water vapor, and that salty glass will continue to absorb water until it dilutes itself to the point it wouldn't get there, or until that glass overflows, which is nice, but it's not useful. Again, this is not yet something that you would mount on your building because it's just going to make itself a dilute, somewhat salty cup of water. So we need more to it. So we're going to introduce the principle of diffusion. So here I take a second cup of water. This starts off as pure water, but I connect those two with a tube. What happens is those will reach an equilibrium in concentration. Let me pause this for a second, if I can. Those will reach an equilibrium in concentration because that solution wants to be balanced in concentration with that solution. That's a diffusive effect, or you consider it through the random motion or Brownian motion, or some people call it osmotic force, osmotic pressure. But all of those are just fancy words for saying that solution wants to have equal parts of salt and water as that one, and if you leave them sit there, they will eventually reach that point. So now we still have 2 cups of salty water. Again, not useful. So what are we going to do with that? Well, what the interesting thing happens is you put one of these and you make it a salt, or a water collector. So we've got this one inside of a space, and then the other one we make a regenerator, or something that's getting rid of that water. So we've taken this and I've added this friendly little sunbeam here in order to heat that up. Just as an illustration, doesn't matter what the heat source is, you just need any heat source. I can't get it to stop. So if you have any heat source, what you're going to be able to do is absorb water molecules here and get rid of water molecules here. If you think that process forward, what happens is you end up with more salt molecules over here per unit of water, or in other words, a more concentrated solution, and you end up with a more dilute solution. So what's going to happen is eventually these water molecules that are collecting here are going to diffuse, we just talked about that principle, over here. So if you follow the path of a water molecule, it was floating around in this room, it went into this cup through that absorption process, the Dead Sea effect. It moved or got pushed over into this side through that diffusion effect, and then the simple addition of a small amount of energy is going to evaporate that in and get that water molecule into the ambient space where we don't mind if it hangs out. So what we've created is a heat-driven humidity pump. And that's what a liquid desiccant is. It's a heat-driven humidity pump. We're adding heat into that system, and we're pumping humidity out. So obviously, this is still not a convenient little box. So what I'm going to do is I'm going to make a sort of an analogy here. Let's call this the processing side. This is where we're going to treat the air that we want to introduce to a room. And let's call this the regeneration side. And this is not necessarily, this section does not necessarily have to be out of doors. It just has to bring in air from out of doors in order to carry away that humidity after that heat has been applied. So if we take that process, and let me see if I can now get this unstuck. We take that process, we're going to stick that into still the 2 cups, and to draw the analogy, this whole blue side is equivalent to what we had as the indoor cup of water, and this whole yellow side is equivalent to that outdoor cup. And this is going to be the processing side where we're treating the air that we're putting into the space, and this is going to be the regeneration side. Now that all still looks, if you're not using a cartoon, it still looks like that, sort of ugly box that we had up there on the rooftop earlier. But what's happening now is it's the same as the 2 cups, but we're adding a lot of stuff in order to accelerate that process, and we're adding a lot of stuff, or a couple of things, in order to get a heat transfer effect that's going to be useful for us. So what are we adding to accelerate the process? Rather than just wait for air to interact with the surface of the water, we're going to bring the liquid up to the top of a media bed. This is like a honeycomb media. And we're going to bring air in under the force of a fan and bring that up from the bottom. You follow these blue arrows, large blue arrows, and we're going to cross flow those or counterflow them in that media bed. This is bringing a lot of air in contact with a lot of the desiccant media. So that's basically to accelerate the process. We're doing the same thing on the regeneration side. So what that leads to is we've got a couple of small circulation pumps, and we've got a fan here, which you can think of as your process fan, or the normal fan you would have. We also have a fan on the regeneration side, which is equivalent to your condenser fan on any air conditioning unit. Well, you also notice that we've got a heat transfer loop here in the middle. I told you in the last slide that we needed a heat source. Well, the beauty is we also want to cool and dehumidify the air, which are both processes that collect heat. So we're bringing in, let's call this outdoor air. We want to cool and dehumidify that air, which we're going to do here. But rather than cool that directly, I'm actually going to chill this solution in a shell and tube heat exchanger right here. I'm going to cool down that liquid desiccant. And this is what we're talking about, a chilled desiccant earlier. Now if I bring it up here, it's both cold and a drying agent. So the air that I'm getting out of the top, once I pass it over there, will be cooler and drier than the air that I brought in from outdoors. Meanwhile, that refrigerant in that system is collecting heat, and we're going to use then a compressor, just like you would in any heat pump, to transfer that heat over to the regeneration side. This is where I need the heat. So I had to do this in order to get the air down to my room conditions, but now I need to regenerate, so I'm going to use the waste heat from the condenser as my source of regeneration. And that's an extremely efficient way, therefore, of making sure this system does not require any external heat input at all. It's completely self-contained. So I've got a heat transfer loop consisting of 2 heat exchangers and a compressor. That's a normal heat exchanger. Or sorry, that's a normal air conditioning system or a heat pump. I've got 2 fans, still off the shelf. This is basically just like a normal air conditioning system. I've got my controller. I've got 2 pumps to circulate a chilled solution, very much like a chilled water system would have. And then I have to make this box. The box is an engineered plastic. It's very inexpensive. It's thermally insulating. And what I've got, in essence, is all the same components, cost-wise, as you would have in a normal air conditioner, but I have a dramatically greater effectiveness at treating humidity as compared to a normal air conditioner. So that's how this is constructed, and that's where you're going to get to a system that doesn't cost a fortune, but has a much greater effectiveness and efficiency in dealing with your overall air conditioning load. Let me pause here while I've got the diagram up. Any questions about what's going on inside of this cartoon here? Well, I'm sure we'll come back to, there's always questions on this one. We'll surface those questions later. Okay. So question came from over here. What are the benefits? Well, there's a financial advantage. That's pretty obvious. You're going to use less energy. We talk about 40% energy savings on your total HVAC load. So we heard 40% energy savings earlier on the fan portion of your HVAC load, which is maybe 15% of your HVAC load. This is 40% of the whole thing. So that's 8 times that amount. This is a very substantial amount of savings. Superior air quality. So remember I talked about those evaporator coils sitting around and gathering mold and bacteria, other microbes? Well, we're actually not only not allowing moisture to form on those evaporator coils, completely dry coils, we're actually actively eliminating through that salt solution any airborne microorganisms that are being introduced to that system separately. Why is that? Well, the Dead Sea is the Dead Sea for a reason. That's because nothing can live in the Dead Sea because it's just so salty. It's a completely inhospitable environment. It's essentially a biocide by being so salty that microorganisms get dried up by the salt itself. It's a proven technology. I'll talk about this in a second. Millions of operating hours and LEED benefits. There's a lot of LEED points or LEED credits that if you're not meeting in some other way, it'll make it available for you to actually satisfy those LEED criteria. So let me review. Cost savings. Talked about a 30, I said 40% before, let's call it a range. It's different applications, but 30 to 50% energy consumption by avoiding the rework. I'm not overcooling and reheating. I'm not heating the air, as in a solid desiccant, and then having to post-cool. There is one process, there's no rework, it's the minimum amount. The systems are sized more efficiently. No longer are you oversizing or adding a lot of refrigeration capacity in order to deal with the humidity on that rainy, hot day in early summer. You have smaller capacity compressors, heat exchangers, etc., due to that fact, and that's what's bringing down your first cost. And then finally on maintenance, we're talking no air filters on that system. That liquid itself will absorb about 80% of the particulate that passes through. The same effectiveness as a MERV 8 filter. And you are also not having to do any evaporator maintenance because there's no algae and muck building up on your evaporator coils. And there's no drip pan, there's no condensate drain, all of the things that are the maintenance headaches when you think about conventional air conditioning systems. Air quality. So I talked a little bit about that biocidal property. I didn't talk about maintaining proper humidity range in a building. So if you look at the different factors, you've got bacteria, viruses, fungus, you've got dust mites, you've got respiratory infections, you've got allergens, you've got chemical interactions, and you've got ozone production. All of these things are affected by humidity in some way. If you look at the optimal zone where you have the minimal amount of all of these, you'll find that it's between about 30 and 55% relative humidity. Very frequently, we'll go into buildings which do not have appropriate humidity control, which are well into the 60 or 70% range, and if you see any visible mold growth in a building, you're probably in the 70 to 80% range. And that is well into this range where you're really exacerbating the problems that these microorganisms can introduce in terms of indoor air quality. I mentioned it's a proven technology. Why haven't more than 7% of the people here heard of this? Well, let me talk about that. We've got background in these industrial processes. What happens is these guys are the early adopters. In food processing and pharmaceutical, you need to have a specific humidity and temperature in order to make sure your process comes out right. And if it's not, you have to stop the whole production line, or you have to throw away hundreds of thousands of dollars of medicine that you produced while it was out of spec. So these guys invest a lot of time and effort into finding all the cool new air conditioning technologies, and they'll implement it. Well, that started happening about 10 years ago. Meanwhile, their buddies in other industrial applications who don't have such a tight spec but still want to actually effectively deal with humidity and efficiently deal with humidity start seeing what these guys are doing, and they say, well, that's a great technology, we're going to adopt that. So it sort of moved clockwise here over into other industrial sectors. And then finally, the people in the more progressive design firms within residential, commercial, and institutional started to realize, well, it's not really just for hitting a specific humidity number, it's the most effective way to hit any humidity number, regardless of what your spec is. So they started adding this in just for energy efficiency purposes. And it starts with some of the types of facilities who have more humidity challenges. I've got hotels here. This is a CrossFit gym. Restaurants have big humidity problems. And into retail, also institutional. You've got a lot of healthcare, nursing home type applications for that. And just general commercial. So we're doing now big box stores and other things like that. So it is still a relatively new technology. The technology literally came from the Dead Sea. That's why I used that graphic and not Great Salt Lake. So it also took a while for this to get over here into the United States. Advantix, I can speak for, has only actively been marketing this in the US for the last 2 years, or 2.5 almost now. But that's a relatively new technology, but it has this background of these millions of operating hours in mission critical applications in pharmaceutical and food processing. So it's very much a proven technology, even though it might not come to top of mind in a general audience. And then the last thing I said about the benefits, there's a lot of lead points available. I'm not the lead expert, but we've got lead points available across all of the categories. And you can actually sum that up to a really substantial amount. Now, if you're getting any of these credits, as you know how LEED works, you can't get that credit double. But generally, we find that people are able to apply for enough to bump them almost a whole LEED level if they implement liquid desiccant on top of what they were doing before. This is just stuff about our company in particular. Let me ask if there's questions. I've got a couple of case studies, which if we have time, I might want to cover, but more interested to pause right now and see what questions you have about liquid desiccant and its applications.
Operating a city maintenance department, which AC and air indoor quality and humidity was a primary concern. What type of training would maintenance folks need to have? Is it specialized training if a city or a school district were to retrofit?
Very good question. Very good question. Okay, so what training do you need? Well, all HVAC techs are going to have the set of training that covers most of this. You know how to deal with fans, control systems. You know how to deal with compressors, refrigerant systems, pumps. This is the new part. It's a saltwater solution. It tastes terrible. Don't drink that. But it's not particularly dangerous. So you don't need any material hazard handling or anything like that. We provide at no cost a 2-day training course for certified technicians that want to become certified on this technology. We ask owners if they want to keep the warranty to have a certified technician, but that's not a racket. We'll train anybody to do it, and the idea is that that's a service that any HVAC contractor should be able to provide for you after the training. Let me think if there's anything I missed there. No, it's very simple. These heat exchangers are a bit of a specialty part. That's a shell and tube rather than a radiator type heat exchanger. So that's a little bit different for people dealing with that solution. There's filters that will keep the muck that you collect out of the air from getting recirculated over and over in the system. That's a preventive maintenance item. You need to backflush those every 2 to 3 months. But it's actually, one, it's more efficient to filter out of the liquid than it is out of the air because you don't incur a pressure drop by doing that. And 2, you don't have to do it as often. Instead of monthly filter changes, which require a consumable part, There is only bi-monthly or every 3-month filter back flushes, which there's no consumable part to add into that system. So it's just going and checking on that.
The working fluid, the desiccant fluid, what is its service life if it's absorbing those other chemicals?
If it's absorbing, 99% of the things that you'll encounter in everyday life don't affect it. The 1% that you'll encounter in everyday life is chloramines in a pool application. And the reason chloramines will affect that, well, let me go back to the 99% first. It's inert. That salt is lithium chloride. Lithium chloride is the chemical neighbor of sodium chloride. Sodium chloride is a very inert, stable substance, doesn't react with almost anything. So lithium chloride is very similar, very stable. The chloramines will become ions when dissolved in there over a long period of time. Now, we've got pounds and pounds of salt in there, and the chloramines you're talking about absorbing grams of it. But over about 4 or 5 years, you will change the chemistry of that solution to where it will become less effective. And we do recommend changing that out in a pool application after about 4 or 5 years. And you can tell by how much effectiveness you're getting out of there in terms of the inlet and outlet conditions. And that costs about, for a mid-size system where you're treating, let's say, about 4,000 CFM, this box you're seeing here, that costs on the order of $700 in order to refill that desiccant.
Well, what's the toxicity of that waste product?
You can dump it down the drain. Don't drink it. Again, do not drink the desiccant. It tastes awful.
For doing typical sensible heat reduction, we talk about degree days.
Yes.
We're sizing them out. Is there an equivalent for vapor?
There's not, unfortunately. There's no good way of comparing apples to apples. And in fact, we often use degree days because in a lot of places, the heat, the overall heat, especially if you're by an ocean, will correlate to the humidity that's in the air. Your hottest days are going to be amongst your most humid. They might not be the most humid in relative humidity, but relative is relative to the temperature. And so they're often the most humid in terms of absolute humidity. But no, there's not a great way to compare that. But what we do, because there's not a great way to compare that, we actually have a simulation that will run this equipment 8,760 hours of weather bin data against the alternative equipment that you put in there, estimated power consumptions, and show you what is really our predicted savings against that piece of equipment.
That's going to be a justifier a lot of times.
It has to be.
Right.
Has to be. And that's, you know, that's the fundamental basis. I talked about 4 benefits. Number 1 is always the key thing. Are we going to get a significant chunk of energy savings if we switch to this? It's not costly. People aren't worried about paying a lot up front and getting paid back. It's just different. And people are worried about not putting on the same piece of equipment or what looks like the same piece of equipment from Trane rather than Carrier, you know, and their next building as compared to the one where they knew it worked the last time. So that's the barrier, and the barrier we need to overcome is, or the way we overcome the barrier is through the cost savings. There was another question over here that I missed.
No, it was basically the same thing.
Okay.
About replacing them.
Oh, replacing the desiccant. Yeah, if just one more comment on that. If there's no strange stuff like chloramines in the air, that desiccant outlives the mechanical components. It's inert. You will spill a small amount of that every time you back flush the strainer. Just, you know, you're going to wash it away. And over the period of 4 or 5 years, that might become a slightly lower level. What we recommend is people have a couple of gallons of this on hand in order to make sure that that's topped off. The way it's controlled and monitored, you don't have to monitor the concentration of this. You're actually just monitoring the level, because the salt never leaves the system. The salt is completely contained within that system. The air comes in contact with it, but none of the salt is carried over into your air conditioning system. So since the salt is always in that system, you can measure the concentration just by measuring the level. And we have 5-position float sensors or 3-position float sensors depending on the unit that just measure where the float is and can tell you when you need to top that off.
What is the,
So there's never an issue of maintenance in terms of, you know, the effects of sludge or anything happening, you know, at the bottom of...
At the bottom of this, if you are in a, you know, people say, if I'm next to a gravel quarry, am I going to have extra maintenance? Yes, you definitely are. What's going to happen is this sump is designed to accommodate where the solution will flow and come to rest before recirculating. That's designed to accommodate some sediment coming out of the air. You're going to pick up particulate, the heavier stuff settles to the bottom, the finer stuff goes into that strainer. If you've got a lot of heavy sediment in the air, an example in Florida is people that live near the Everglades, which start on fire and there's all this ash in the air. You need to perform a process similar to a cooling tower scrub where you just remove the media, and in this case you remove the desiccant, you pump that out into a separate container, and then you just scrub the bottom of that thing out. We haven't seen anybody that's needed to do that more frequently than every 5 years or so. That process is something where you have to take the top off the unit, so it takes about 2 or 3 hours to execute that. Good question. There was another one over here.
Material on the heat exchanger, piping, and honeycomb media.
Very good question. This is a salt water solution, so everyone thinks corrosion. Corrosion is going to happen unless you make all of these wetted surfaces an engineered polymer, which is what we've actually done. That's the real trick. Anyone can make this box. It's kind of like a hot tub, I like to say. It's got, you know, heaters and fans and pumps, and it's a big tub with a solution in it. But the real trick is you've got to transfer heat effectively, and you've got to do that with a plastic. So this is a proprietary part, and that part is a heat exchanger that we developed over the course of years, which is a shell and tube heat exchanger, copper on the inside, but epoxy-coated copper, and then the shell is going to be a polymer, a reinforced polymer that goes around the shell part of that. So that's a epoxy-coated copper. And actually, a lot of the engineering went into how do you test those to make sure that that coating didn't get scratched and it would have a reaction that would cause it to eat away at the copper. So we have a impedance test that we perform at multiple times, and you can do this even in the field to make sure the coating is still integral on that heat exchanger. And then what were the other things you asked about the materials?
The piping and the honeycomb media.
Piping is polymer tubing. Honeycomb media is corrugated cellulose. Unique thing about that corrugated cellulose, and I tell people that and they think, okay, it's tower fill, I need to replace it every 2 years. What is happening in a cooling tower, or what happens to any wood fiber, what degrades a wood fiber is two things, either ultraviolet light or microorganisms, specifically mold. Mold is what eats wood fiber. Well, I've got a biocidal solution constantly washing over that media. There's no mold growth whatsoever. There's no UV because it's inside. That honeycomb media actually will usually outlive the mechanical components in that system, even though it's only a corrugated cellulose. The only thing, actually, the lifetime is determined primarily by the binder in that cellulose. So we have to buy high quality corrugated cellulose with good binder. Yep.
Do you all test the air coming out of the, I guess what you call the supply,
yep,
for any salt?
We do. That is the biggest concern, and rightfully so. And not only is it the biggest concern because you can start to really cause problems downstream of this system, it's also something that other manufacturers of liquid desiccant did a poor job at, was letting what's commonly called carryover of the salt, so that you're getting a salt solution downstream of this unit. And that causes all kinds of problems, corrosion and issues with your duct, and things start to fall apart. It's awful. So our fundamental design philosophy is all of the salt had to stay in that system. So you'll see at the top of this is just a cartoon, but I've got a header that's bringing the solution onto the top and just flowing this in a very smooth, controlled way onto the surface of that honeycomb media. That honeycomb media increases the pressure drop. An alternative could actually be to spray this with atomizing nozzles. And that's what other liquid desiccant companies will do. What happens though, in any spray, the finer particulate, you notice this is a counter draft, the finer particles of the liquid desiccant actually just get carried away. It's not that the salt will actually evaporate and then recrystallize downstream. The vapor pressure of salt is so extremely low that basically physically doesn't happen. But salt can get carried away if there's any spray or any turbulence of flow or anything like that in this area. So the tricky parts of engineering this are, okay, you've got this heat exchanger, and now I've got to get that media bed so that there's a laminar flow over a film of water, that film of water on the surface of that media. And that's why cooling towers use the same media. They don't think about it as heavily as we do, but it's just to reduce the spray coming off of that. But we've managed to reduce that spray down to a level that's completely undetectable, even with the most sophisticated equipment. So we have done and are willing to do again, whomever you want to test that, ion chromatography on that, on the air coming out of there, and you can detect down to 5 parts per billion, and no detectable amount of that solution is coming out.
Is that the same on the outside?
It's the same on the outside, absolutely. It's the same process. So we've got that media bed exactly for that same purpose. And you don't want to lose the desiccant over time either. It's not just carryover. You don't want to lose the desiccant. You don't want to change the chemistry of your system. Other questions? Let me talk about a couple of case studies. And I think it'll make the benefits a little bit more tangible. This is a school. I don't have good energy data because we just treated one part of the school and it wasn't sub-metered. But the really interesting thing about this one is this was a school that was having an odor issue. Basically, they weren't controlling humidity very well. So they basically had an unpleasant odor, and that unpleasant odor was created by mold that was living in that classroom. So what we did is we did a pre and post test of the air in terms of the mold content. And what happened was we installed one small unit, this is only 800 CFM, to treat a couple of classrooms on the upper level of a school where the humidity problem was. And we were able, with that small addition, to reduce humidity to a controlled level below 50%. And what happened was they previously had about 377 mold spores per cubic meter, which is a relatively high number, not astronomically high. But following that, we did a test where there was actually only one mold spore once you would install that system in an entire cubic meter. And by the way, it was even hotter and more humid outside. In other words, more mold spores in the airborne surroundings than there was when you did the first test. So it's basically a 99% reduction of airborne mold in that room. The students and staff were more comfortable. The temperature set point actually was able to be set up because people were more comfortable now that it wasn't so humid in the room. And it got rid of the odor entirely. So that's one example of the impact in terms of air quality benefits. This is a nursing home. I showed you that this is actually the nursing home where we stuck one in the closet. I already talked about that one a little bit. Let me talk about this. This is just a storage of perishable goods. Duty-free Americas, you might have seen these stores in airports that you visit. They have these distribution centers with all their perishable goods. You can see a picture in the lower left-hand corner. And they've got one, for example, in Miami. Big overhead doors opening every hour. A lot of humid air coming in. They were having a pretty big humidity problem, and their conventional system was dealing with that by dripping water all over their expensive perfumes, chocolates, and all of this stuff. So obviously that's a terrible, terrible outcome for them. So we were able to reduce the humidity, but at the same time, because we're reducing the humidity, we got a 35% reduction in energy consumption. Dealing with that humidity in a more effective and efficient way both gave them the indoor temperature and humidity constraints that they wanted, but also reduced their energy consumption. Now it's maintaining conditions 73F and 45% relative humidity, which is perfect for their perishable goods. And there's no humidity, no condensation issues, 35% energy reduction. So that's a, just an example. I've got other stuff. This is a hotel in the Caribbean. This room looks familiar because we're sitting in one very much like that right now. But basically they had a lot of difficulty bringing in enough fresh air in that humid environment in order to ventilate their banquet halls. And in this one you can see we don't have the energy measurements, but they needed 18.4 tons on average of chiller capacity for that space. That reduced to 11.7 tons once you dealt with the humidity in an effective way. Okay, I've got some other stuff, but that's probably too much information already for today. That's a lot to digest. So who's interested in liquid desiccant air conditioning now? Come on, gotta have a little bit more than that. All right. Well, we have some material up here. There's actually some case studies I didn't talk about. Also, I want to point out Dion and myself are going to be here. If you have any questions, just come up, want to discuss it, discuss applications you have. We're happy to talk about it. Be as unbiased about liquid desiccant and the general technology as possible. And thank you for your time.
Thank you so much, Trevor. This was a fascinating presentation. We've seen everything today from solar systems to now liquid desiccant systems. Again, talking about the different systems, the different options, the different technology. We hope this has been very informative for you. We hope you've enjoyed yourselves. We hope you've enjoyed breakfast, and we hope you've enjoyed lunch. But most importantly, we hope that you are leaving with a good deal of information that you could possibly apply in your future projects. We're really struggling here to implement sustainable practices, but today we've been provided with 3 different wonderful options. So we hope that you do engage the speakers. Mr. Wende, Trevor is here so that you can continue conversations with him. And again, thank you so much for being with us today and for taking the time to come and spend half a day learning about the different sustainable practices in HVAC. We hope that you join us again for future presentations. Our next presentation will be April 4th, and we have another one on April 20th. But before you leave, I do want to ask if you would please fill out the survey. These surveys are very important to us and to our speakers. We need to know exactly how interested you are in furthering your education in subject matter such as this. And if you have any comments, if you could please add those. Our interest is really to know whether these workshops are beneficial to you, whether you are actually taking any of this information and applying it in any form or fashion. These programs are here thanks to the generosity of our sponsors, and without their generosity we could not be providing them to our campus and the community. I don't know about you all, but we have had tremendous budget cuts. There is no longer any budgets for travel, and so we're working really hard to bring you very good sources of education here at UTPA so that you can get that type of education through these programs. In order to continue these programs, I need your support by filling out these surveys so that our executive directors and administration understand the benefit of these type of programs. So thank you once again. Please fill out your surveys, and if you have any further questions, please stick around. We hope that you enjoyed networking with each other, and we hope you will join us again. Thank you so much.